Hey everybody, welcome back to the Professor's Du Bois channel. This is Corey and Victoria, and we're going to be doing some equilibrium calculations today. This is actually episode 4 in a series we're doing, and this particular problem we're going to do uses an algebraic technique, for lack of a better term, that
It's a pretty good term.
we're going to call it the FOIL method. And so we're going to do an entire problem, but the focus of this video is working through this FOIL technique. So let's get started on this problem.
Okay, so in this problem that we are going to be going through is we are going to be using an ICE table like we often do for our equilibrium calculations, and we are provided with a K value, and the question is asking for what the equilibrium concentrations are for all of the species. And we did this in the previous episode as well, and this just has a little bit like a further step in the algebra that's required. So we want to walk through this reasonably slowly, so feel free to speed us up if you understand parts, and then slow us down for the parts that you need help with. So we are going to represent our equilibrium expression here. K equals our products over our reactants. All of them are being included in the expression because they are gases. We don't include liquids and solids. And we've set up our ICE table here. And the amounts that we are provided with are, we have amounts for both of our reactants. And this is in a 1 liter vessel, so our moles equal our molarity. And remember that your ICE table has to have the concentrations. So our initial concentrations are provided for our reactants. They didn't say that we had any product, so we're going to assume that we started with no product.
Now, did we get any equilibrium concentrations provided?
No, it just gave us our initial. So we have to represent our equilibrium concentrations in terms of X. And our products, we know our products go up because they started at 0. It's the only place it can go. And so we know our reaction is going in the forward direction. Our reactants are making and forming products. So our reactants are going to go down by X. Now there's no number in front of the X because the coefficients of all of these species is 1. So it's just X. If we had two carbon monoxides, for example, it would be minus 2X. But these are all 1, so that's going to actually make things a little bit simpler. We're provided with the Kc. That just means that it's formed using molarities or concentration. Sometimes we have gaseous reactions in terms of Kp. That means that the K expression was calculated using partial pressures of the gases, but these are in molarity. So we've just plugged in our equilibrium concentrations that are in terms of X.
All right, so I have to multiply these two terms in the denominator here, and this is really the focus of this video, is using this method we're going to call FOIL. Now, FOIL is fun to say, and what it stands for is first, outer, inner, and last. You get it? The FOIL? Got it. So what does that mean? I mean, okay, I get it, but what does that mean? What we're going to do is we're going to take the first term. So over here in this parentheses, it's 0.364. That's the first. Over here, it's 0.364. So I'm going to multiply those two together. That's the first step I'm going to do. And when I do that, I get 0.1325. Okay,
Right.
so far?
Yep.
Okay.
Now we can do the outers.
Outer. What does the outer mean? Well, that's the outer part. So that's going to be for this one, like if we look at this, like, let's say,
you can highlight.
let's say, okay, let's say this is the inside, right, of the whole thing. This is the inner. And then I could say that these are the outers over here. How about that?
Good.
Is that helpful?
Mm-hmm.
Good. So I'm going to do the outers first. So that's 0.364 times a negative x, or minus 0.364x. That's the outer. The inners are in yellow. So that's 0.364 times a negative x minus 0.364x. And then lastly is the last term. So what I mean by that is if I call this the first over here, the minus x would be the last. So this is the first, this minus x is the last. So I'm going to go negative x times negative x, which is going to be a positive x squared.
Nice.
Okay, I have like terms. This is an x term here, and this is an x term. So I'm going to combine those. I'm just going to do that now. So this is 0.1325, and I've got negative 0.364x and a negative 0.364x. And if I combine those, I get a negative 0.728x. I just added those together, plus x squared.
Just put a single line maybe through the things that are now gone. So this is all still just what we've turned the denominator into that.
Yeah, so we're still working on this part of the formula here. So this is in the denominator, and the next thing I'm going to do is I'm going to multiply both sides by this big long term. So over here I'm times 0.1325 minus 0.728x plus x squared cancels. If I do that on the right hand side of the equals, I have to do it on the left. And this is another distributive property, right? I gotta multiply 77.5 times each of those terms.
Why don't you rewrite it? I think that would be helpful.
I will.
77.5 times all of those terms.
It's going to be 0.1325 minus 0.728x plus x squared.
And that equals x, because we still have that numerator up there.
All right, I'm just going to scroll a little bit. So now what I'm going to do, what I mean by distribute, is I'm going to take this, I'm going to multiply by this, I'm going to multiply by this, and I'm going to multiply by the x squared. So first thing, 77.5 times 0.1325
is 10.27.
Next step, 77.5 times a negative 0.728x minus
negative 56.42x.
Now I'm going to multiply 77.5 times x squared
plus 77.5x squared. That's a lot of x squareds. And we still have equals 1x. Let's call that 1x.
I like it. Let me make that 1 look a little more like a 1. Not great.
Looks like an L.
Okay, so, yeah.
It's okay.
So, I need to set this side equal to 0. The thing you want to be careful of, you don't want to divide by 1x. Because if we divide by something by itself, it equals 1. But we can set this to equal to 0 by subtracting 1x. So 1x minus 1x equals 0. If I do it on this side, I have to do it on the other side. Now, this is my x term, so I'm going to go minus 1x.
The reason he wants to set this equal to 0 is because we have an x squared term, an x term, and just a number. So that means that we need to use the quadratic equation or the quadratic formula in order to solve this equation. So when you do that, you set everything equal to 0. Bring all of your terms to one side equals 0, and then you can look at what you have and find the a, b, and c term. And the a term is the number that's in front of x squared. Now if it's just x squared, it's 1. And the b is the number out in front of the x, and the c is just the plain old number without any x's. Now be careful and make sure that you use the negatives, and the signs that are with that. So our b term is actually a negative 57.42. A is 77.5. Didn't we subtract? Oh, that was the x term.
Yep.
And our c is 10.27.
So I actually just used a quadratic equation solver online, and it gave me two roots, and they were 0.439 and 0.302. And what'll happen is one of these roots just won't make sense. So let's take a look at the 0.439. Over here, if x equals 0.439, this makes sense. 0 plus 0.439. Okay. But look over here on my reactants. 0.364 minus 0.439, that would give me a negative number. And we're not going to have a negative number. That doesn't make...
Negative concentration? That doesn't make any sense.
Doesn't make sense. So our correct root, or our x, is our 0.302. So we're looking for these equilibrium concentrations. Now I'm up here. And my COCl2 is just x. This is the equilibrium back from the ice table. So x is 0.302. My Cl is 0.364 minus 0.302. And that's going to be 0.062. I got that point. What I did is I put this value in, my x, in for x. So I went 0.364 minus 0.302. Same thing for the CO. That's going to be 0.062. And there you go. We have our equilibrium concentrations.
A good thing to do once you've solved for equilibrium concentrations is put it back into your K expression and make sure you get that K.
Yeah.
So that's a good check.
And you notice here, the K was 77.5. So K is greater than 1. This is quite a bit greater than 1. So that's going to be a product favored reaction. And our product is the COCl2 phosgene.
Nice.
And you can see, I mean, look at the concentrations at equilibrium. Now, we could test this. We could put the 0.302 in here, and then the 0.062 for the CO and the Cl2. We should get 77.5. Yep. I'm going to leave that up to you guys to test out. And if you get something different, leave a comment down below, and we'll
fix it.
And we'll fix it. So
that's right.
There's an example of where we actually used the FOIL method. That was our purpose. We wanted to go through that slowly, but we also had to distribute in there, which is good. We had to use the quadratic equation. And
good question.
We got our equilibrium concentration. So
we still have a few more videos in this series, so make sure you come back and look at the next episodes in the series to get more algebra and more solving equilibrium calculations.
More to come. Stay tuned for episode 5. Thanks for tuning in.